In this video, we're going to cover the first 3 sections of Chapter 9. So, Chapter 9 is all about algebra. And we're going to first start out talking about numerical expressions. Okay, numerical expressions only contain numbers. So, read the rest of what I have written here. But these are numerical expressions. They don't have variables in them. So, a key point, though, is that they are expressions because they don't have an equal sign. They are numerical expressions because they only have numbers. If it has an equal sign, it's going to be called an equation instead. So this is a key point. Make sure that you can determine whether something is an equation or an expression. Okay, when you try to evaluate or interpret numerical expressions, you have to use PEMDAS correctly. So what exactly is PEMDAS? So PEMDAS says that we do parentheses first, we do exponents next, we do multiplication and division in the order that they come, okay? So if division comes first, do division first. If multiplication comes first, do multiplication first. Multiplication and division carry the same power or weight, just like addition and subtraction. Do that in whatever order they come, because addition and subtraction carry the same weight. Okay, doing PEMDAS correctly is key. Okay, as we go further down this page, let's see what else is important. Another thing that's important is to know what terms mean. Okay, terms are connected by either an addition or a subtraction. So that's why this is one term and this is another term. So you want to know that just so you are aware of the vocab of algebra. And I have some other things about evaluating numerical expressions. So I give you some examples of how to solve it. And the key thing is, as you work down your page, you want to line up your equal signs and always follow PEMDAS. Okay, this is kind of an interesting page because what they have you do is figure out different ways you could estimate or really calculate the number of dots in the diagram without actually going through and counting the whole thing. So the first way I did it was to do the following. I divided this kind of right here and here. And then I said, okay, the top half, so this half right here, ends up being, oops, sorry, let me do that again, 1 plus 3 plus 5 plus 7 plus 9. Okay, and then I have the top and the bottom have the same exact format. And then I'm going to add the 11 more dots that are kind of in the middle there. So that's one way to get the correct number. Another way to do it is to look at it this way. I have 1, 2, 3, 4, 5, 6 rows, diagonal rows, that have 6 dots in them. So that's 6 times 6. And then I have another 5, 1, 2, 3, 4, 5, that have 5 dots. So I can add up that. Either way, I'll get the exact same number. Then when they come down to this next little piece, and make this a little bit bigger for us, they want us to figure out an expression. So what I did was I divided here, and I divided here, and then I said, okay, this is a 3 by 5, and this is a 3 by 5. So I have 2 3 by 5s, plus I then have a 4 by 8 in the middle there. So plus a 4 by 8. All right? Then they want us to explain how they got this interpretation. So I thought this is pretty clever. What they did is they continued the count down here and up here. And they said if this is all filled up, you would have 10 times 8. But it's not really filled up. then you've got to subtract away the 2 blocks that had 3 by 3s in them. And that's how that gets explained. Okay, so then the next method was pretty clever as well. So they said, let's do this. Let's have these 2 pieces. And here's the other piece. And so each of those boxes are 7 by 5s. So I have 2 7 by 5s. But then notice that they overlap. So you've got to subtract away the overlap. All these different methods will get you the correct answer. And it's nice to be able to see it different ways. It's really good for your students, and it's really good for you as well. So let's do this last one now. So this last one, it says, write 2 different expressions for the total number of dots in the dot design below. Okay, so I did the following. I first did 10 by 10. So I said, what if you made it 10 by 10 and ignored the fact that you had that gap in the middle? And then you can subtract away the members that would have been in the gap. So that's one way you can do it. Then another way is I did this. I divided it like this, and I said, okay, this is a 3 by 10, and this is a 3 by 10. So I have 2 3 by 10s, and then I have a 4 by 4 here, and another 4 by 4 here. So I have to add 2 4 by 4s. Okay? So I hope you enjoyed that. It's very fun to look at these diagrams and figure out how many different ways you can actually add them together. All of this involves math sense and kind of thinking about math in your head to figure out which way your brain sees it the most clearly. So let's go on to the next page. So here what they're doing, there's a handshake problem I wanted you to look at. And I have a video right here, so you can just put that video, copy it to your browser, and look at that. There is a formula for the handshake that's going to make your life so much easier. So they did a very nice job, I thought, with little Lego cubes that they visualized what it would be like if you had 35 people shaking hands. So mathematically, you can figure it out. Once you see a lot of patterns, this is what it is. If you have 35 people that are going to shake hands, and everyone's shaking hands one time, whatever the number of people that you have, take that number times 1 less than that number and divide it by 2, and you will get the same number they got in the video. So what if I had a different problem? What if I had only 20 people shaking hands? Then I would say 20 times 19 divided by 2, and I'm going to get 190 there. Okay, how did I do that so quickly? I said 2 goes into 20 10 times. 10 times 19 is 190. Okay, so it's nice to know another method than just straight up counting to get the answers for some of these problems. Okay, so let's continue with this activity 9C. I kind of blew it up. I hope you can still see it. It's in your back of your textbook. It's on page 162. So they want you to figure out, is there a way to do a shorthanded method of adding odd numbers? So first let's do the long-handed way. So 1 plus 3 is 4. 1 plus 3 plus 5 more is going to be 9. This is going to be 16. This is 25. This is 36. And this is 49. Now, if you look at that, you may say, wait a second, they are all perfect squares. So if I have 2 odd numbers and they're in sequence, I'm going to have an answer of 2 squared. If I have 3 odd numbers all in sequence, that's 3 squared. 4 squared, 5 squared, 6 squared, 7 squared. That is a nice pattern. And that is what's special about the solutions, okay? That you have the number of terms that are odd from the beginning to when you end, and then you just square it and you will get the sum. So based on your answer in part 2, predict the sum of the first 100 odd numbers. So isn't that going to be 100 squared? Because the number of odd numbers you have, and it says the first, so you know you're starting from 1, and that's how you're getting 100 squared. Okay, so let me just make this a little bit smaller again so I can read the last question. And the last one says, based on your answer in part 2, predict the next sum. Okay, so what do we have? We have odd numbers from 1 to 99. So what is that going to do for us? So think about that for a second. So if you think about this, you're going to have 5 numbers from 1 to 9. You're going to have another 5 numbers from 11 to 19. And another 5 numbers from 21 to 29. If you keep following that pattern, you're going to realize that you're going to have 50 numbers. So the summation is going to be 50 squared. And those are neat little tricks of math. Okay, I thought this was a good problem as well, and I got it from class activity 9E. So it's very, very important to know when working with fractions when you can cancel and when you have to be careful. So when doing multiplication, so this is important. They've given you all of these examples. They are not all correct. Let's get rid of the ones that are incorrect. Okay, look at these two together. They are the same problem, but we have different answers. Why is that the case? This is a multiplication in the numerator. Since it's a multiplication, when you cancel and put 6 into one of them, you are done. Do not do that. So 6 goes into 36 6 times. 6 times 96 is 576, and that is correct. Now, when you have an operation that's an addition or a subtraction, this is addition right here. Notice that these two problems are the same. You have to put the 6 into both numbers because you really could write that fraction as 36 6 plus 96 6. So you have to reduce both parts of the numerator. Okay, both terms have to be reduced. You don't have 2 terms here. Remember, you have 2 terms when the numbers are connected by addition or subtraction. You have 2 terms here. This is done correctly. This is not done correctly. Okay, so B and C are the ones that are done correctly. Let's go on to the next page. Okay, so there's a lot of key points in here, so you can read through this. We talk about that algebra allows us to summarize and reason about an infinitely many calculations, and that's because you use a variable to represent something, and so that allows you to reason more cases. So I defined a variable here. Okay, it's a letter or some other kind of symbol that represents something else. And the example I gave was a circle, and R represents the radius length of the circle. Okay, then they had a little section in the textbook that I thought was valuable. If you say a tank of water has 55 gallons in it, the variable W could be used to represent the gallons of water. But you're not going to say W equals water. You're going to say W equals gallons of water so that you clearly know it's a number and not the concept of water. Okay, so going on, how do we work with expressions with variables? So you can work with them in the following ways. An algebraic expression is a meaningful string of numbers and or variables, operations, and or grouping symbols. Okay, you've got all kinds of things going on here. Now, you can only group like things. So if you had, say we had x plus plus x plus 7. You could call that 3x plus 7, but you can't call that 10x. Okay, so be careful about that. It goes on here. This is writing an expression this way. Notice this is an expression and not an equation because there's no equal sign. So the big thing about this expression that they wanted you to pick up on is that you have coefficients in front of the variables. So you have a 15, you have a 1 hiding there in front of the y, you have a -4 in front of the x cubed. So remember that terms are connected by addition or subtraction. So we have 3 terms, and each of the terms has a coefficient. The 1 in front of the y you can think of as a hidden coefficient, and that brings us to the next page. Okay, evaluating an expression is an important thing to understand. It means that when they give you the value for the variable, you plug it in and get the numerical answer to the either expression or equation. So in this case, it was an expression, 5x plus 2y. Wherever I have an x, I'm going to put in a 3. Wherever I have a y, I'm going to put in a 4. And that's going to now give me something, it equals something. So I'm going to make an expression into an equation once I introduce that equal sign. And the sum ends up being 23. So we can use this compact expression, 5x plus 2y, and we can define x's in another way. So why don't we define them like this? Given that definition of my x's, I have a whole different answer to my equation once I develop it. So I'm going to have 5 plus 10, so that'll be 15. So here's a compact expression, and then here's an evaluation of the expression given values for x and y. Okay, when we're talking about equivalent expressions, they have to be exactly the same regardless of what you plug in for the variable. So if you have 3x's added, that's equivalent to 3x. Okay? That's not equivalent to x cubed because you're adding them, not multiplying them. Be careful when determining if expressions are equivalent. So for example, if you distribute your 3 here and here, you do indeed get 3x plus 21. They are equivalent. You cannot distribute a square. When you have x plus y times another x plus y, your equivalent expression is going to be x squared plus 2xy plus y squared, and not that. Okay, so that's why these two expressions are not equivalent. Okay, so here class activity 9F had some good problems, and here's the first problem. So it says there are J liters of juice in a vat. Someone pours a third of the juice out of the vat. Which of the next expressions gives the number of liters of juice that remain in the vat? Okay, so J minus 1/3 is not good. Okay, so let's talk about what is good, and we'll figure that out. Okay, this one is good. This one is good. This one is good. Why is that the case? Because I have 1j minus 1/3 of the j. That's my expression. Over here, I don't have a j here, and that's why that's incorrect. For b, if I distribute that j, I get j squared minus 1/3 j. That is not what I want. So C, D, and E are all equivalent. So look at them closely and make sure you're comfortable with that. Notice that here they have a dot for multiplication. Here it's just next to it. That is equivalent. Okay, so activity 9G also has additional problems if you want to look at that in the back of your textbook. So this is an important concept that I wanted to point out. So if they ask you, this is a practice problem, if they say draw, label, and shade a rectangle so that it gives rise to the equivalent expression of x plus 3 times y plus 4. Okay, so that's going to be equal to this if you expand that. So how can I express that as a rectangle? What you do is you take one side of your rectangle right here, and that is going to be x and a 3. Okay, the top is going to be y and a 4. So look at the areas that you are developing. This light box is x times y. That matches the x times y. This light green is 4x. That matches this 4x. This light green is 3 times y, which matches that. And the dark green is 3 times 4, which matches that. So be able to do this exercise. It's very important to connect a binomial multiplication, which is what that's called, to an area problem. Okay, it's a very big starting point for many of the fundamental math problems that deal with this kind of multiplication. Okay, so in 9.3 they talk about equations. So we already said that equations have to have an equal sign. Now, there's different ways to use equations. This is one way. Here's another way. The second way is setting two expressions equal to each other. All right? So you don't want to tie in the idea for your students that an equal sign always means to calculate an answer. That's not the case. Okay? So be careful how you use that. So let's see for this, if I said calculate an answer, you can't really get an answer in the traditional sense. What you can do is solve it and get a value for x. So you're going to get x equals something to make that true. But it's not really like saying 5 plus 2 equals x, so 7 equals x. Okay? So it's not always used like that. An equation is not always that simple. So some equations are identities. So this is demonstrating the commutative property. A plus b is the same as b plus a. So you can say 7 plus 5 is the same as 5 plus 7. There's no solution required. You're just stating a property. Some equations relate quantities that vary together. So quantities that vary together are also called formulas. Okay, let's go on to the next page. Okay, sometimes you have to solve an equation in order to solve a problem. So here's a word problem, and word problems are indeed the meat and potatoes of math. So this is from your textbook. So it says Tanya had some money. After she spent $5, she gave half of the remaining money to her mother. At that point, Tanya had $18. How much money did Tanya have at first? Okay, so first off, you need to figure out how they set this up. So T is for Tanya's money at the very beginning. She spends $5. That's why it says T minus 5. Then whatever she had at that T minus 5 point, she gave half of it to her mother. So divide that in half. And at that point, she has 18. Okay, so can you figure out how much money Tanya had at the very beginning? There's a couple of ways to do it. The easiest way is to multiply the left side by the reciprocal of 1/2, which is 2/1. Whatever you do one place, do it again the other place. So you end up getting T minus 5 equals 36. Add 5, and Tanya had $41 at the beginning. Okay, so does this make sense if I work backwards? If I plug in a 41, 41 minus 5 times 1/2, does that indeed equal 18? And you will find that it does. So I know that I have solved that correctly. Okay, here is a very visual way to find expressions that are equivalent. So look what they're doing. They're using a pan balance. So you start out by saying, okay, this pan on the left has this amount of blocks. This one has 2 blocks and then some other number in the box where the question mark is. So how do we handle that? So you can do a guess and check, and you can see that if you put 8 in this little box, it's going to be too heavy on the right side. So how can you think about this? So what I would tell you to do is this. I would say, okay, this is my setup over here. Do you see how I have these 2 blocks right here? That's like the 2 blocks there. So what I would do is I would get a pile or a little column of 3 and another column of 3 and put that right here, and I'm going to be balanced. And then you can check your work at the end by saying 8 equals 8, and yes, it works. So that's a very visual way to do it, and a lot of classrooms will even have scales that you can do this math, so the kids have a good sense of what they're trying to do and how you're balancing expressions. So we're going to do a couple of these. We don't have a balanced pan to do these, but there is a way to think these through logically, and I apologize for this being blurry, but this is on page 169 in the class activity part of your textbook. So in case you can't see this, this says 382 plus 49 equals x plus 380. So think about the balancing pan. Do you see how I have a 380 here and I have a 382 here? What if I took 2 away from the 382 and gave it to the 49 instead? Wouldn't that make 51, and wouldn't that balance things out? So that's how I would think about it. Okay, so look at this next one. This says 7, the dot means multiplication, and then you have x plus 5 equals 7 times 38. Okay, so let's think about this. They both have 7s. In here, I have a 5. Over here, I have a 38. How do I get from 5 to 38? I'm going to add 33. Okay, so that will get me balanced. So the next one, we'll do a couple more. This is 23 plus 36 plus x equals 24 plus 36. Okay, so go for the matching. This matches this. Ooh, 23 is 1 less than 24. Therefore, this x must be 1 to balance that out. Okay, so this last one is interesting, so we're going to do this one too. This says 23 times x minus 36 equals 46. So that's kind of interesting. So how do I want to handle that? Well, when I look at it, I see that 23 times 2, because it's times something, gives me 46. So how do I make what's in the parens 2? Well, what if I made x 38? Wouldn't that do it? Wouldn't that make it 2? So without doing a whole lot of distributing and calculating and using calculators and trying to add things up, you can really reason this out by thinking about the balancing pan and try to balance out your equations by doing these little manipulations as I've done. So let's do the last page now. Okay, so what's going on here? What they do here, and I want you to look at it, is they take you through a whole balancing pan activity or pan balance activity. And what's nice about this is they give you the pan balance, but they also give you the equations. So I want to have you have some time to look at that and make sense of it. The goal is to figure out what plain old x equals. And what you're allowed to do is you can take equivalent things away from each other. And by manipulating the pan, they have done that. So see if that makes sense to you. They end up getting x equals 3 at the end of the problem. And they get the exact same answer by doing the algebra along the left. And that ends this video.